the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 68, where today we have special guest John from Epic Math Time. So, John, maybe you want to introduce yourself a little bit to our listeners here today.
Well, my name is John from Epic Math Time.
Yep.
So on my channel, what I like to do is I like to express myself as creatively as possible about whatever I find interesting in mathematics. So whenever I first started, I kind of had like ideas that I wanted to do, but I was very limited to what I could actually create. And just over time, I started really getting into like the graphic design and the video editing. And now I feel like I'm really like unlimited in how I can express these topics. So that's why I really like making videos. It's just an unlimited form of expression. And I really think that video learning is going to be a big part of the future.
For sure.
I really do.
Yeah, I also noticed that you put like exercises for the viewers at the end of your videos,
yeah.
which are definitely awesome, right? Because, you know, most of the learning is in applying what you
it's in doing.
learn.
Yeah, that's right, absolutely. And that's really important to me. I really like to give exercises that build off what was covered, or maybe allow people to express their thoughts for the topic in a certain way, and it drives some interactions in the comments, which I like. So yeah, that's something I always try to do. I don't always put them, but if I can think of something good, I always do it.
And do you think of them yourself, or do you like see some questions online and you're like, oh, that's a good...
No, I always think of them myself.
Oh, cool.
But sometimes I think of the exercises before I think of the video.
Oh yeah.
So like I think of exercises, just random things,
and kind of like shape your video around it. Like that's
that's
kind of
right.
nice. That's kind of nice.
Yeah.
That kind of sounds cool. Like thinking about the
Yeah.
problem before how to explain it. That must be nice. Well, I mean, we're definitely gonna dive into what Epic Math Time is and where it is, because I think like especially with as you were mentioning, the graphics gotten so crazy, especially after that whole new revamp. It's gotten crazy. So like real props to you. So like we're gonna get into
Thank
it.
you.
But before, let's get into some news. Let's
For
get
sure.
into the comment of the week. Okay, so for today's comment of the week, we got Cosmo Cube, and they say, "Love this kind of content." Thank you.
Thank
Keeping
you
it
so
plain
much.
and simple. Thank you, Cosmo Cube, for that wonderful comment. As always, if you want to be featured in this quick segment of comment of the week, all you have to do is comment, and there's just a random pick really, and you can be featured in the comment of the week section.
Definitely. So in terms of downloads this week, we are now up to 155,000 downloads over all platforms. So thank you everybody who's been listening to the podcast, downloading the podcast, and sharing. I think now we're at like 10.4 thousand in comparison.
We're at 10,500 already.
Yeah, that's awesome.
Yeah, it was crazy. We hit 10,000 so recently, and we're already at 10,500. Like,
And that's on Spotify.
That's on Spotify only, yeah.
So make sure to follow the podcast. Make sure to subscribe on YouTube, where you can actually see our faces.
Yep.
The only place we post the videos on YouTube. So if you want to go check it out, definitely go there, subscribe, and all of that stuff.
Or go to Instagram, math.physics.podcast, where you can also see our faces, our clips, our thumbnails, all our updates posted there first and only. So go check it out. And for that wink wink giveaway, that's happening soon. Don't worry, it's still in the making. We haven't forgotten about it, obviously. It's going to come. It's just a lot of preparation for that. Even though we're hyping it up so much, it's not gonna be that hype. But it's obviously the very first one. It's gonna be crazy, for us at least. So just bear with us. And that's the news of the podcast. Maybe we can get into it now.
Cool.
So John, usually in these episodes with any guest, we have kind of a classic way of starting them with what I like to call the classic question, to ask you, how did you get into your respective field? So John, how did you get into math? What was that spark?
When I was really young, like a kid, like, 5 or 6 years old, I was really into math. And the most a kid like that could be into math. And I guess like elementary school kind of crushed that out of me because I didn't care about math at all by the time I was in high school. Zero.
Wow.
0% care. None. I graduated high school, didn't care about math. Went to college, didn't know what I wanted to do.
Oh wow.
Oh, I wasn't sure if like I cut out or something.
No. I was just
Reacted.
surprised. I'm like, oh wow, like
Oh,
completely
oh,
clueless
yeah,
on
no.
math, and then
This is
now where you are.
common, by the way. This is common. Yeah, that's right. So, high school I didn't care about math. Went to college with no notion of what I wanted to do. So I still didn't know anything. Then after a couple years of just like drifting through college, I decided I wanted to major in physics. So I had to switch to a different university and major in physics, and that's what I did. And then I had to, I got to the point where I was doing labs, and I hated labs. You see, I really liked physics, but I don't want to actually like do it. I just want to, I just want to think about it and solve problems. But like doing the labs, no. And I was double majoring in math at this point, and then I just switched to just math, and that's what I ended up getting my bachelor's degree in. But yeah, it was a long time for me to like rediscover that thing that I liked when I was a kid. Like I didn't see calculus until I was probably like 20 years old when I first saw calculus.
Wow.
So yeah, definitely late to the party, but I'm trying to make up for it.
And what kind of courses did you take when you initially got into college?
Initially college or initially like math?
College. Before math.
Ooh, I don't know, man. That was in 2008. So, just, the standard introductory stuff. My major, I think, was business administration for a while.
Okay.
And then it was, I don't even know. I switched majors so many times.
So it was something basically that you took just simply because you had to take it, not
Yeah,
because, okay.
yeah, that's right.
So it's
Yeah,
kind of like,
that's right.
okay. So then where did that physics thing came from where? Because you said you just switched to physics. Where did that's pretty
Yeah, it was
big jump, from economics or something?
I think that I always kind of had an interest in that sort of stuff. And it just it's hard to explain, man. It's like it never occurred to me that I could just study that in school.
Yeah.
It's hard to explain, but like I guess one day I had that realization. I think a little bit of it is that it's intimidating to go into physics or math or a field like that instead of something more normal. Because like I didn't know anyone that was doing that.
Definitely. And do you still are you still interested in like the theoretical side of physics? Or...
Oh yeah, absolutely.
Okay.
Yeah, I mean, I don't know much about it. I mean, comparatively, I'm not. I don't know as much as a physics major.
For sure.
Yeah, an undergraduate physics major. I know a bit. Mainly things I'm interested in and how it connects to math, that kind of stuff.
You spoke about like non-science courses like right now as normal, and I'm really intrigued by that. Because I think I can classify you as a teacher, right? Like as a teacher, is that a correct?
Sure.
Because I guess I mean you educationally you teach on YouTube, I assume. So as a teacher, like what is your stance on like kids thinking, like students thinking that these courses are like not normal? Like is there a reason for that, or is there just like a fundamental notion that prevents people from going into the math and science? Because a lot of people skip out math and science just because they're like, oh, it's too hard, or oh, I can get more, real life out of something else, not really knowing the, still severe implications of where math and physics can take them. You know what I mean? So
that's a really good question. So I think a large part of this is that math for sure is kind of mischaracterized as a subject. There's an essay by a mathematician named Paul Lockhart called A Mathematician's Lament, and he basically argues that math is more of an art than a hard subject. Math is not a rule-bound subject. That's a wrong stereotype. Math is a very creative subject. So the fact that it has some uses and applications kind of sucks because it makes people treat it like this useful, rigid, rule-bound thing when it's really more like an artistic expression when you get down to it. So I think the problem with it is that it's kind of sitting in this line, and its true nature is like more of an art form. It's like a poetry of ideas, but then at the same time, it's taught into this. It's taught as this rigid, applied, rule-bound thing. It's like fitting a square peg in a round hole or whatever, however that expression goes. And not to say anything against applying math. It's just that in the book he says, Paul Lockhart says, music has been used to lead armies, but that's not why people write music.
Yeah.
They don't say, "Oh, some people are gonna march to this one day." This is not what they're doing.
Yeah. And one thing that is super interesting to me, and I've done this before, is go and ask people who don't do like higher level math, right? They kind of stopped at before calculus and things like that, and ask them, what do you think like graduate degree mathematicians do? And their answers may surprise you because like to us, we're like, oh, it's more like abstract stuff, whatever. But to people who haven't like who stopped at like high school math, they think it's just like harder operations. Like you just keep learning harder operations and then you just keep solving problems, but it's really so different, so incredibly different.
I think that I think that never really ends. You don't know what you don't know. So when you try to, imagine what the progression, you tend to take what you know and just complicate it.
Yeah.
So like if you ask a kid about this, they'll probably think it's big numbers, right?
Yeah.
Calculations with really big numbers.
For sure.
But if you ask someone that's like in calculus, they might think it's really hard derivatives or something, Like I don't think that this necessarily stops. And then even for myself, like what a modern, abstract algebra researcher is doing, I probably can't really imagine exactly what they're doing. Maybe I could sort of get a hang of it if I read into what they were doing, but it would take a while. It's just I can't really imagine where the field is going without knowing about it first,
Yeah, and what kind of sucks is that it's so like every branch of math is so like specific that it's like, especially at like the cutting edge, part where like research is being done and things like that, you can't really know something about everything or like deeply understand something about everything. So you kind of just have to pick and choose, and then kind of, you can do some reading, I guess, but you'll never really be like understanding as much as the pros that
especially with like undergrad level math. Like I mean, being first-handed experience, like we know that second year mathematics, even like at the same level of first year mathematics that we took, is basically first year mathematics, just like very, very more abstract, taken to a multivariable level, right? So as you were giving that example of that high school student or whatever stopping after calculus or before he really knows anything and he's thinking about these numbers, like, yeah, we're also doing a very similar thing and just taking it to, okay, let's do the same thing that we did this year, but just, as you were mentioning, like kind of complicate it further and see what happened if we make it even more abstract. So I guess the thing here is, well, how much more can you complicate it, right? Like a simple... I guess we're still finding out, but maybe, John, maybe this is a question more apt for you. Like, how much more can a function? I guess this is a very abstract question, very, very vague question.
I'll try.
But like, what is the level of complication that we can really go to? Like being a graduated math student, like, is there more complicated math specifically?
So I can try to answer what you're used to and how that gets complicated, but also I want to point out that people often say that math is like it builds upon itself and it's like this linear progression. That's totally not true. Okay, like for a math major, like you'll probably know a lot of math majors, but after you take like the calculuses and then like a proof introduction class, the calculuses are mainly to give you, some sort of mathematical maturity. But after you learn how to write proofs, it's just a branching, you topology, abstract algebra, this, that, and the other thing. And you can take one and have no idea about the other, and it doesn't matter. Like, knowing one will help the other, but it's not always a progression of complication. Now, when it comes to calculus, y'all are in multivariable calculus. So, let me think. Functions can get a lot more complex in the sense that they don't need to be functions of, just real numbers or sets of real numbers.
Functionals, right?
And calculus in general. So, calculus can be done, or an abstraction of calculus can be done on a lot of different types of mathematical structures. They're called manifolds. So, R2, the real number, the real plane would be an example of a manifold, but if you can think about the surface of a sphere, also known as a sphere. A sphere is only the surface, but that's a manifold that you can do similar things on. So it's not always about just complicating things. And in fact, to some degree, it's about simplifying things. And whenever you abstract something, you're really kind of simplifying it in a certain sense.
I guess that is the other way. I guess that is a nice way to look at it. Like, it's not really complicating it. In fact, so by going into the more abstract, you're actually simplifying it. That's a nice way to think about it.
Yeah. So another thing is that some people might think of things that are abstract as not having any application, but that's not true, because whenever you make something abstract, what you're doing is you're kind of removing the superficial details from it. Okay? So when you do that, and you have this abstract creature, it's like, oh, what is this even talking about? Well, it's talking about whatever is modeled by that situation. I always think of, y'all know Lex Friedman?
Yeah,
of course.
Yeah.
Okay, so I always think of a conversation between Grant, 3 Blue 1 Brown, and Lex Friedman, where they're talking about higher dimensions. And Lex Friedman, great guy, but he seems to be under the impression that dimension has to mean spatial dimension. And in this conversation with Grant, so he mentions higher dimensions maybe being this esoteric thing, and Grant's like, no, these can be highly applicable. And he's like, it's a common misconception that higher dimensional mathematical structures are only applicable to a universe that's that many dimensional. But that's not true, because a dimension, the math does not care what the dimensions represent. So you could think of there are 4 macronutrients: protein, carbs, fat, and alcohol. And you could make a vector space out of those 4 things. That's a 4-dimensional vector space. And a food is a vector, a 4-dimensional vector, and a diet is a group of vectors. And if you want a calorie count, that's a linear transformation into the real numbers. Like, the math does not care what these things are representing. So when things are abstract, it means there are a lot of applications. Anything that can be described by this mathematical structure, it can be applied there. The math does not care when it's abstracted, if that makes sense.
Yeah, definitely. And my physicist brain, when you, like, the example that you went into was great, but I was thinking of, like, you could have like a vector where it's like XYZ, the position, and then the velocity XYZ, and then you have like a 6-dimensional vector, but it's still describing something in 3 dimensions, but you just use these.
Right.
Yeah.
Yeah, there are 3 spatial dimensions, but a dimension, in the sense that the mathematics is concerned, is basically just like a continuum of values.
Yeah.
Like Pokemon have attack, defense, special attack, special defense, and speed. So Pokemon are 5-dimensional. Those are 5 independent. I think that's all of their stats. But yeah. Yeah, the math doesn't care if the dimension represents spatial dimensions or the amount of protein in a food. It doesn't care. So when you abstract it, it no longer cares about the superficial details. So in that sense, abstracting things it makes it more applicable to more things, because all the superficial details have been, surgically removed.
Interesting way to think about it. Damn, that's really an interesting way to think about it. So continuing on this journey of your college experience, after your whole physics to double major to pure math change that you did over there, what after you graduated? What was the situation then? What was next for you?
I worked a couple jobs and ended up going to grad school for a long time. And then I put that on hold recently. Grad school's tough to stay in for a long time. You know, you're ready to get out eventually.
Mm-hmm.
So, yeah.
Is grad school a
And-
lot of like studying as well? Or is it mainly
Yeah.
just, as they say, just writing papers and stuff? Like, what's the...
No, it's a lot of studying. The material gets way harder really fast. Like
Wow.
the first year of grad school was like, okay. Then it started to pick up, and it started to pick up even more. And yeah, it gets pretty difficult.
And did you go to grad school just for math?
Yeah.
Okay, cool.
Any advice for, I don't know, just grad school goers, like soon, if anyone is graduating this year, maybe next year from college, any advice to them going into grad school?
Yeah, I would say make solving problems and studying kind of a social event with your other grad students, because it's more fun that way if you're like hashing out problems with each other, sitting around, because math especially can be a very social thing. There's a lot of inside jokes and all this stuff happening with math, and there's funny stuff. I mean, I'm sure y'all are aware of that. So I think it's a fun. It's fun whenever you have other people involved with you.
I can see
And here's
that.
an interesting question. So obviously in elementary school and middle school and all that stuff, your math class is just, learning operations and things like that. Do you think that maybe learning like proof techniques and maybe like set theory, but just like obviously very like elementary ideas that like you learn in college, but maybe would have been a lot more useful to learn earlier, just so you're kind of comfortable with what math actually becomes later on?
Yeah, so first of all, kids in elementary school are certainly capable of learning basic set theory.
Definitely.
I mean,
Yeah.
I think that's definitely true. I think this still goes back to the whole mathematics as an art thing, because right now, math is basically designed to be this conveyor belt of how to like apply the problems or solve problems by applying math, but it's almost as though if there's a difference between using math and doing math, because I think of mathematicians as sort of being like programmers, except their programs are theorems and results and stuff. So whenever someone uses the quadratic formula, they're using a program. But I really don't know if I would view that as doing math. I think that's using the program. It's like that doesn't... Programming might be more fun than using Microsoft Excel. I mean, so it's kind of like there's a distinction between using the final product, which are these formulas and these theorems, and inventing a problem and trying to think your way through it and coming up with a general solution. I mean, just the fact that we can know the roots of a quadratic from the coefficients only, that's interesting, but that's just like, no, whatever, here's the formula.
So like using the code versus writing the code is basically
Yeah,
what
exactly.
So like writing the code is the whole well, I think that's actually a bang on explanation of what math feels like doing, because I have like some experience, because like I like to dangle my feet in a little bit of coding here and there. And I think like that's almost the exact explanation, like perfect explanation of how you can describe math to someone else. Because
that's
usually,
how I feel about it.
yeah, as you were like, it's perfect, because usually people think of math as the programming thing. So they think of, okay, I'm just gonna use things that have already been made. What's the point, right? People get bored of that. Like, why would you learn something if it's already been created 300 years ago and it's just being used? Like, what's the whole point of that? But inventing it is the whole new thing. It's just like writing that code. That's that powerful point.
That's solving the problem. If there's a... And I don't mean you have to be the first person to discover it. I mean
Of
an
course.
independent discovery. Like, imagine if you were like learning about derivatives for the first time, and you would like, I wonder if there's a way to get with the product, or a function that is of the form of a product of two other functions. What does that derivative look like? And maybe you're checking some cases and stuff, and you're like, oh, it looks like it's this. Can I prove that? And then you end up with the product rule. That's a lot more that's more mathematical than saying, here's the product rule, apply it 20 times over and over again. Like, that's using the program. But discovering it for yourself and improving it is a lot more fun. And it's less stressful, too, especially if you don't put a time limit or anything. If you just allow yourself to think about things, it's less stressful.
For sure. And what changes or like additions to the curriculum or subtractions from to like an average like middle school math class?
Yeah, I don't know, man. I'm not gonna presume that I'm qualified to describe how education should be, but I envision it treated more like an art where it's not treated as this subject that everyone needs to know and is compulsory to learn all these formulas and stuff. Like, I don't see the point of having people having the memory of all these formulas that they hate. Like, I don't see what the point of that is. So more exploratory, and I try to do that with my students. Like when I taught geometry, I want them to discover it's fun to get the area of the triangle, like the formula for it. It's fun to see, if I cut it in half, then I rearrange it, it's taking up half this square it makes. That's fun, and they can draw pictures and all that. But the problem I found when I did that is that they're so used to it being taught the other way, where like, here's the formula, practice, that they get frustrated with themselves, and they don't feel free to try stuff, if that makes sense. Like, I wanted them to just think about it and explore, but they feel judged if they don't know what to do right away. And it's like, it's so procedural in their mind. And I guess part of the reason why I have this view of it is because, like I told you guys, I did not care about math throughout high school. So it's almost as though the education I had when I was in grade school didn't stick. So like, I only think of math in this way. I didn't get the procedural. That didn't stick. So I don't know. Some of it's very bizarre to me when I'm teaching and I see how it's normally taught. I just feel like it needs to be treated more like an art form.
Especially with YouTube, like you can definitely, with today's level of YouTube and today's level of reachability, like you can really do exactly what you want and show it how you want to show it. And then everyone just looks at that exact same thing that you're teaching. It's like teaching the world, instead of teaching 3 kids. And like, I mean, it might be really nice, right? Like, I mean, assuming, do you get any like, I guess fan mail or stuff from this, your whole YouTube shebang that you have going, especially now with those upgraded studio, anything?
I get emails from people, asking a lot of questions and stuff. I don't know about like fan mail.
No, like, yeah, questions like that. Just like, just asking questions about like the topics itself that you might want to talk about and, stuff like that. Because that's, I guess, at the end of the day, who you're trying to help, right? Like you're trying to help those people.
I get stuff like that. And another thing, if you ever go in my comment section, there are some frequent commenters that I'm not teaching them. They're at least peers. They're like they're very knowledgeable, and they write these long, very thoughtful comments, and I love that because, like, even though I'm the one on the screen and all that, I don't have all the answers. I'm not like, I'm not like preaching to people. Like, I feel like a lot of my viewers are peers, at least peers in some cases. So I don't know if I would view my channel as meant. I'm sure it educates people, but I kind of think of it as more of like a math fan channel. Like, just, just the stuff that I think is interesting. Yeah. If other people find it interesting and they want to talk about it too, that's cool. But like, a lot of other people are doing a great job doing the educational thing. And, I don't know if that's exactly where I'm headed. Someone in the comments said I was the PBS space-time of math. That was like the best compliment ever. So like, that's kind of what I'm going for,
No, but that's
like,
pretty
PBS
valid though. I
space-time.
mean, with your goal and looking at the type of videos that you have, they're kind of sprung around very just kind of interesting topics here and there, not like a whole playlist kind of a thing. So like, totally, like that.
Right, exactly.
I mean, you're enjoying it, so why not?
Yeah.
Right?
The only challenge, that's exactly right. The only challenge is that it's a lot harder to present a math topic in a way that's generally interesting the way it is physics, because physics, I mean, you can talk about stars, you can talk about all these physical things, but math, you need a background just to get to the interesting part. So that's a pretty hard challenge to overcome. Like, I don't know if y'all have ever seen the meme where they're talking about how, like, there's like a chart and it has like physics shows and it has like Cosmos and it has all these cool shows, and it gets to math and it's just like there's nothing for math. Yeah, exactly. Yeah, exactly.
Those are always, yeah. I know those are classic, because I guess it is a little, but I guess, I mean, why not, right? You could start that space, because especially with improving graphics day by day and stuff like that, like it looks like it's going somewhere in positive direction, hopefully. So, good stuff. Well, as you were talking clearly, about making math more interactive, interestingly enough, you guys should go check out today's sponsor, Brilliant. So Brilliant, interestingly enough, this very month of July, they have made their courses a lot more interactive. Their algebra courses, their mathematic fundamental courses, a lot of which we were talking about in today's episode, it has become a lot more interactive. So instead of only reading and then, question answer, very similar to the exercises, you're now actually interacting with the course, and then you're doing that whole exercise part at the end. So they've added some pretty cool new features, especially with, kind of today's topics. They have some really cool courses in linear algebra, multivariable calculus, that whole shebang. So go check it out. Link in description below.
Yeah. So for the first 200 listeners that go and sign up for their premium membership, they will get 20% off. So make sure to go click that link in the description and start learning math. But John, I had a question in my head back when we were talking about your school experience, and what was your favorite math course that you took?
In undergraduate or ever?
Undergraduate,
okay.
Big one.
I would have to go with, I think I would go with like an introductory topology course.
Topology course.
Yeah, topology, because that's a very new concept, and like abstract algebra, it's abstract algebra, but topology is something that, like, you don't see, or you don't know that you're seeing. You're seeing it very early on. You just don't call it topology, Like, for example, I can give an example. So, a set. I've mentioned this on my channel before, but like a set, okay? A set does not have a shape to it. A set's just a bag of crap, So like the real numbers is a set. When you draw it as a number line, that's the topology of the real numbers. That's additional information. The shape of it is the topology to some degree. It's a little looser than that. But sets don't have a shape. So whenever you tell a calculus student to draw the real R2, or, the Cartesian product of the real numbers, the plane, the fact that it's a plane, that picture is coming from the topology of the set. It doesn't come from the set. That's just... So these concepts are really always there, but taking that to a new level, and it's really a new topic, more so than the others, at least among the classes that I took.
So what were kind of some of the groundbreaking, like, topics that you learned in that introductory course?
Okay. Well, so this might be a little awkward to describe, but so when you have mathematical structures of different kinds, there are functions between them that preserve their properties. Okay, for in linear algebra, if you have two vector spaces, a linear transformation is the kind of function we're interested in. Well, in topology, the kind of function you're interested in is continuous functions. And what's so cool about that is that that's not a new kind of function. That's a kind of function that you've always been studying, like in calculus and all that. So the fact that topological spaces were the spaces that we were always kind of interested in for a lot of the math we've been doing is really shown by the fact that continuous functions are what preserves topological properties, if that makes sense. Because continuous functions, I mean, that's everywhere. When you take a derivative of a function that's continuous or differentiable, it's continuous. These are common concepts, and topological spaces are what those functions are always mapping between.
When I think of topology, I always think of a torus for some reason.
Every single time. I knew it.
Yeah,
I knew it.
That's a topological space.
Yeah, 'cause it's the classic. It's that classic thing, right? It's the classic shape.
Yeah. So why a torus?
I think it's like the coffee mug thing, but that's a little bit overplayed.
Maybe,
I do understand that. I remember watching like the Vsauce video where he does talk about like where you continuously like reshape it.
Like how many holes does a human have? Something like that is the name of the video.
Oh yeah, he tricked a bunch of people into learning topology. Man, I don't think these headphones were designed for my head shape. But anyway, so no, a torus is interesting. So this is what I like to say about the torus. So think about a two-dimensional video game like Pac-Man, where the map warps you to the other side. So if you go all the way to one side, you end up on the other side, and if you go up, you end up on the bottom, right? Well, that's a torus. Topologically, that's a torus. Think about it. You're looping through the top, and you're looping around the side. So you can think, oh, it's a circle this way, and then it loops that way. So you could think of games like Pac-Man as taking place on the surface of a torus. You know, the topology doesn't care about the shape of it. It cares about the fact that, when you go to this end, you end up back over here. You go up, you end up over here. A game like, like Asteroids, or like, some game where you're in a spaceship and you can go to the side and up here, there, and then you're going up all the time. That might be like a cylinder or whatever. But yeah, these are all examples of topological spaces. The fact that you warp to the other side on the game map is what determines the topology, not that it's on a 2D screen. Yeah, if that makes sense.
And I remember learning about, like, just on my own, not in school, about like the way you can represent topological spaces with like the square with the arrows. Yep. Where you like match up the sides and all that stuff.
Yeah, exactly.
I also, maybe if you can give like a little clarification, but I remember learning about the Klein bottle and how I believe it's a 2 manifold embedded in 4D space.
That's right.
Okay.
Well, so it can be embedded in 4D space. Okay. That's not like an intrinsic thing about the Klein bottle.
You know, maybe you want to explain the Klein bottle to those who haven't heard it before.
Yeah, so the Klein bottle is a 2-dimensional manifold, and what that means is that if you go to any place on it, it looks like a plane. Okay? So like any surface is a 2-manifold, because if you look at a little spot on it, it looks like a plane. Okay? Now, what's interesting about the Klein bottle is that it's non-orientable like the Mobius band, and it's also closed. Now, so let me make sure I say this in a good way. Whenever a topological space is closed, that sort of means that it doesn't have an edge or a border, but at the same time, it doesn't continue on forever. I'm trying to roughly describe this. So think of a plane. That would not be closed because it goes on forever. But if you think of a sphere, that would be a closed 2-dimensional manifold because it doesn't have a border or an edge, and at the same time, it doesn't go on forever. Okay? And then there are non-orientable manifolds like the Mobius band. Now, the point is that either of those two conditions, being non-orientable or closed, means that you need one more dimension to embed in Euclidean space. So, what that means is that the Mobius band, can you put a Mobius band in 2 dimensions? So it is a 2-manifold, but can you put it in 2 dimensions? No. You can't, exactly. You need 3 dimensions. Well, the Klein bottle is non-orientable and closed, so we need 2 more dimensions. So both the Klein bottle and the Mobius band are 2 manifolds, 2-dimensional manifolds, but the Klein bottle needs 2 more dimensions for Euclidean space to have an embedding.
I swear I saw a video of a Klein bottle, though. Does that not exist?
Well,
so
yeah, go ahead.
I can say so you can't represent a Klein bottle in 3 dimensions. But what you can do is what's called an immersion, which is like a less strict representation. And what that's going to look like, it's going to look kind of like a Klein bottle, but it's going to intersect itself in a place where the actual Klein bottle doesn't intersect itself.
Oh, now, that's why it looks like that.
Yeah, it doesn't actually intersect itself in that spot where it intersects. And a good analogy is if you draw a picture of a cube on a piece of paper, there are going to be lines that intersect that don't actually intersect on a cube, right? If you think of like the normal drawing of a cube, there's going to be lines intersecting that are actually different sides of the cube. It's kind of like that. Whenever you take that Klein bottle into 3 dimensions, it's kind of like you're drawing a picture of it in a space that doesn't have enough dimensions, so that intersecting itself is just like the lines of the cube that intersect.
Yeah. So just to make it look like a 3D thing, even though it really isn't.
Right, you're forcing it to intersect itself.
Yeah, and the same thing goes with the Mobius strip. Like, you can't draw a Mobius strip and it be like the actual thing, right? Because it's just gonna look like a line's just crisscrossing.
No, that's a perfect analogy. Yeah. We can't take the Klein bottle to 3 dimensions. We can't take the Mobius band to 2 dimensions. Exactly.
Yeah, but it's a fun like mathematical object to own. You know.
Yeah.
Oh, for sure.
I want one. I need to get one.
Yeah,
for sure. Even the Klein bottle is like a classic thing in my opinion. Like, you know, even though I guess as now I just learned, it unfortunately does not exist in these 3 dimensions. But so increasing in topology here, like, I'm assuming we see a lot of linear algebra embedded into a lot of these higher dimensional abstract math topics, right?
Well,
or does it kind of lack as you?
So I'm sure that happens, but I actually think of it more in terms of abstract algebra. I think I'm more familiar with connecting topology to abstract algebra, and you know, I can talk about what groups are in a second. But with topological spaces can be associated to groups. You know, for each topological space, it has what's called a fundamental group. So we take the topological space and we associate to it this group that allows us to say things about the topological space. And it's always nice to transform problems from other fields into abstract algebra problems, because it's a pretty neat subject. It's very organized and structured, you know. So, but I can tell you what a group is if you want.
For sure.
Let's hear it. Let's hear it.
So,
I'll hear it.
So
yeah.
So I'm gonna mainly talk about finite groups, but so all a group is, you got a set and you have a binary operation. That just means, you know, an operation. You take 2 things and it spits out 1 thing, like addition. That's a binary operation. So it has to be associative, there have to be inverses, and there has to be an identity element. So for example, the real numbers with addition, that's a group. Addition's associative. There's an identity, 0, and there are inverses. Every number has a negative. So it's a very abstract sounding thing. Well, an example of a finite group is the symmetries of an object. So let me see if we can see my phone. I've been doing a lot of hand gestures that cannot be seen. So the symmetries of my phone, you know, I can do this, I can do this, and I can do this. All those things together, if I combine them all into a set, that's a group under the operation of combining two of those symmetries.
By the way, for those listeners, it was a quick rotation on all 3 axes. What
oh yeah,
because we have a lot of listeners, so they might have not been able to see this and this, right?
Right, I forgot.
Yeah.
I totally forgot about that. Whoops. Yeah. Okay. Yeah, I'm just you know, moving my phone around in a way that doesn't change its position, basically. So at first it seems like that's a very specific kind of group. You know, the symmetries of an object, that's a group. Well, it turns out that every group is isomorphic, so basically every group is the same as a subgroup of a symmetry group. And all that means, ultimately, is that every group can be considered to be a group of matrices. Okay? That makes sense. Like, a group of matrices under matrix multiplication. Every finite group can be represented that way. And you're like, okay, so what? Well, you guys have taken linear algebra, right? So what does a matrix represent in linear algebra?
Linear transformation.
Exactly, it's a linear transformation. So if I take any group, I can think of that as a bunch of linear transformations. So in a certain sense, every group is describing the symmetries of something, because if I look at a set in that vector space that's invariant. Oh, I should have said square matrices. They're all square matrices.
Okay.
Because they need to be invertible.
Right.
Yeah, they need to be invertible. So think of a vector space, a function from a vector space into itself. So every group can be represented as a group of these matrices. So if you think of a set in the vector space that's invariant under all of those transformations, the group is describing all of the symmetries of that set. Does that make sense?
Okay, yeah. So
So-
I'm thinking about like the rotation matrices and
That's
all that
yeah.
stuff.
That's
Yeah.
exactly what was
Right.
in my head.
Right, exactly. So if you just think of a set lying in your vector space, and if I apply all of those matrices to it and the set maps to itself,
Mm-hmm.
then it's invariant under that linear transformation. Then that object, that set, is its symmetries are being described by that group. So it turns out that every single group, despite the fact that it's just this abstract thing, it's a set with an operation, all of them are describing the symmetries of something. And how complicated the group is can determine what dimension vector space you need to have this object being symmetrical. So for example, what about modular arithmetic? Y'all looked at that a little bit?
Not really.
Not
No?
really.
Okay.
Nope. Not at all.
So the most simple group, besides the trivial group of one thing, is a group where you have, let's say we have 0 and 1. That's our only objects. Okay. 0 is the identity. 1 plus 1 is 0. 1 plus 0 is 1. So it's a very simple group. Well, you might ask, what are the symmetries, or what object is that the symmetries of? And it would be a line, right? Because a line, an infinite line, what can you do? You can do one thing. You can either leave it alone or you can reflect it, right? And if you reflect it twice, you're back to the identity. So that's like 1 plus 1 equals 0 in this group.
Oh.
Well, flip plus flip is you back where you started. So every single group like that is describing the symmetries of something.
Oh, wow.
Yeah.
So that's the
and-
idea behind these groups.
Yeah. Y'all have heard of the monster group, right?
Yeah. I don't quite
Yes.
remember exactly what it is, but I watched the 3 blue 1 brown video on it.
Yeah, he did a great job in
Yeah.
that video. So, yeah, the idea is that, okay, first of all, the monster group comes from this special class of groups called simple groups, finite simple groups. And it's the largest in this category called sporadic groups. And none of that matters that much. It's just the fact that this group exists. So, like I said, it must be describing the symmetries of something, right? So what is this giant group describing the symmetries of? And I don't really know. I've read about it, but I don't know what it's talking about. But it's related to some operator that I think is involved in string theory. So
Whoa.
yeah.
Wow.
So it's like if you look up monstrous moonshine or something like that, it'll talk about it. But every group is describing the symmetries of something, which is kind of interesting because it comes from this very abstract thing. It's just a set with an operation, and it's not clear why this is describing symmetries of stuff, but they all are. Finite
But what's the
groups, at least.
purpose of something like this?
So that means that whenever you're studying group theory, you're kind of studying the whole concept of symmetry at once. So one place this might be applied is in chemistry, because the orientation of molecules, that's important. Chirality, all that stuff, that's all group theory. They'll have chemistry majors doing stuff with character tables, which is ultimately something from group theory. So anything where symmetry is involved, it's group theory. Yeah.
And for some reason I was thinking about like vector spaces and subspaces. Is it a thing where you have like a group and a subgroup?
Yep.
Okay.
Absolutely, and it's pretty much the identical concept. Yeah,
And
if you have a set that's closed under the binary operation. So, for example, if I can give another example, the natural numbers with addition, that's a group. A subgroup of that would be the even natural numbers,
Right.
because you add 2 evens, that's
Yep.
another even.
Yeah.
The odds would not be 1 because the identity's gone. 0 is the additive identity, and it's not odd, so that's not a subgroup.
and
Okay.
also,
And also, too. Sorry, go ahead.
would let's say you have just like a simple group that like you can kind of say like, okay, it represents the symmetries of this object, and then there's a subgroup of that group. Would the objects be related in some way?
Yes, that is a beautiful question. That's a really good question, dude. That is a great question. Yeah, so I have a good example. But I think I forgot the details. There's a certain group called, I think it's S5, and I think it's S5, but basically, it's not defined to be the symmetries of anything, but it turns out it's the symmetries of an icosahedron, and one of its subgroups a three-dimensional icosahedron, and one of its subgroups are the symmetries of the shadow of the icosahedron.
Oh wow!
So yeah, no, your intuition is exactly right. That's right. Yeah, they're going to be related. When you have a subgroup, it's a subgroup. It means it's a piece of those symmetries. It's some of those symmetries. So it's describing maybe a simpler object like the shadow of the icosahedron. But
That's awesome. That's awesome.
Yeah.
So shadow, as in like you can also mathematically think of it as projection, right?
Yeah, exactly.
Oh, so you can even apply it there. That's pretty cool. So how these elements are related. So you were talking. So a fundamental idea in group theory, as you were talking about, are these binary operators that connect them, right? Are the ones that are able to satisfy the whole group identity. And in your most recent video, I think this was a question long time coming that you might have suspected. In your very most recent video, the new binary operator, the new operator that you had found, quote unquote, the power log. Maybe you want to talk a little bit, because I thought that was a super cool video. I don't know if you're the first one to ever think of that, because I couldn't find anything like this online.
No, what I do is whenever I have an idea like that, I do not try to find it, because if I end up finding it, it just kind of takes the steam out.
Right, but I couldn't, so I strongly believe that's a you idea.
I was able to find it. There's not a lot about it. I was able to find it after I started looking it up. It was hard to find it because I didn't know what it was actually called. But
so you wrote the code and then found similar code is what you did.
Yeah, that's right.
Okay,
so
that's good
they're
stuff.
called the commutative hyperoperations, and they were presented by a mathematician, I think, that I never heard of. He doesn't have a Wikipedia page in like 1915, but it's not talked about much. But yeah, so what was your question about it? Sorry.
So we were talking about these binary operators that connect these groups. So I just want, and you said the word binary operator, and it made me think of this in your latest video. So maybe just a quick intro on what power logs are, because I think they're like, again, your concept really cool. And more importantly, I think how they connect to group theory, because that was my major question. But again, for the people that probably haven't heard of power logs, you might want to give a short description.
Yeah, I totally made up that word.
Yeah, exactly.
So I involved ring theory in this, but ring theory is a related subject to groups. It's just there's two operations now, and one of them distributes over the other. So it's like multiplication and addition. But the way that happened is that I noticed that logarithm property had like some symmetry to it, so it looked commutative. So I was like, okay, maybe this is a cool operation. And it did all the cool things I wanted it to do. Since we found that it has an identity, we found that there are inverse elements, we knew it was associative, we showed all those things, and that makes it a group. If you take the real numbers, or the positive real numbers with the power log operation, it is a group. And then what I was wondering is the fact that it distributes over multiplication made me think, okay, is this operation playing the same role to multiplication as multiplication does to addition? And the way we end up showing that is we show that the ring with addition and multiplication, so you think of this algebraic structure, is isomorphic to the ring of positive real numbers with the power log and multiplication. Now what isomorphic means, it's a fancy word for saying they're the same mathematical object. All their differences can be thought of as just completely superficial. So I think of it as like changing the font, So like if you have let me think of an example. So I mean, y'all have done isomorphisms in linear algebra, and isomorphisms are very strong in linear algebra, because if you have two vector spaces of the same dimension over the same field, they're isomorphic. It basically means that the only difference between them is that the elements look different. So what we showed is that these two rings are the same. That means that the power log is, or you can think of it as two languages, and we translate one language to the other. The multiplication gets translated to the power log, and addition gets translated to multiplication in a certain sense. So that confirms that they're exactly the same relative to one another.
But you do still have to translate like the real numbers to the positive real numbers in order for it to work.
That's right. Yeah.
So a very powerful tool, the power log. So I think one thing though that you kind of missed in the explanation is the whole big thing. I mean, obviously we're actually going to probably link the description, the video below for those who want to go and watch it. But the biggest thing with the whole power log is that it is to multiplication what it is to addition, right? With that whole and it kind of takes exponentiation's place almost.
Yeah,
which
yeah.
is what you kind of wanted it to do.
Yeah, so in a certain sense, it takes exponentiation place. Like, I was kind of being hyperbolic. Like, exponentiation is the next tier up for multiplication in the normal sense, but this is still the next tier up for multiplication in a different sense. But yeah, this new operation is the next step up in the sense that it is exactly to multiplication as multiplication is to addition. It's exactly the same, you know. So it's the exact same algebraic relationship preserved. And one of my exercises was, okay, we can get this new operation by kind of going in the opposite order. We ended up finding this isomorphism with e to the x is like the translator code, you know? Mm-hmm. So I was like, okay, so we can use this function to get the new operations. So can we take the natural log, you know, that's e to the x going the other way. Can we get negative tier operations? And you can. If you go natural log and you just keep carrying the operation that way, you can get the -1 tier operation, you know, that's below addition. And what I found is that if you take this limit, like if you keep bringing the operation down, it turns into the max operation. So it just tells you the maximum real number out of the two real numbers you input. Because maximum is another binary operation. Yeah, so that's like the negative infinitieth operation in this sequence is max of A and B.
Is there a reason, or that's just what happens when you go all the way down?
The reason is that we keep applying this mat over and over and over again, and what it's doing is that we have the exponential nested inside a bunch of times. So when we input these two values, one of them they're both going to blow up, but the fact that it's a bunch of exponentials means that whatever difference there is, it's going to be super magnified. You know what I mean? Like if you have e to the x, you know, and you look at you plug in 2 to it and you plug in 8 to it, that's going to magnify the difference, right? The difference is going to be much bigger than the difference between 2 and 8. One of them is going to be, you know, moderately large number. One of them is going to be a huge number.
Right.
And you keep doing that, so it's changing the difference so much between these two numbers, so that one of them basically becomes irrelevant and the other one's blown up out of control. But then you have a bunch of natural logs outside, so it just wipes it all out and brings it back down after making one of them irrelevant. That's kind of what's going on there.
So in the limit, it just reduces it right back to just the biggest one.
Yep, wow. That's right. Yeah, in the limit. Yeah.
Wow, it's kind of beautiful. It's kind of almost beautiful.
Yeah, I thought it was cute.
And
it's kind of cool.
And I'm guessing if you go the other way, it just goes to infinity.
I didn't see anything happening, and some commenters solved that. It seems to be that it doesn't do anything interesting, like in the other direction. It doesn't. In other words, it doesn't approach anything. It just keeps kind of like blowing up out of control in a certain way.
Interesting.
For sure.
Interesting. Well, yeah. That's basically I think all the major discussion topics that we had, right?
Yeah, for sure. So I mean, I learned a lot about group theory today.
I think so.
I'm definitely more interested in, you know, excited to get into, you know, higher math topics now.
Oh wait, y'all are physics majors, right?
Yeah.
So okay, let me explain. This was adorable. This is a cool little link between group theory and physics. So you know how in special relativity, there's a certain way that velocities add.
Mm-hmm.
Yeah.
Y'all have learned special relativity stuff. Yeah. So the speed of light plays a certain role, right? The role that it plays. Let me try to gather my thoughts on how I want to say this. So if you look at all of the possible speeds from -c to c, just think of we're in one dimension and this way is a speed, that way is a speed. So we're looking at the set of real numbers from -c to c, whatever c is. It's playing the role of the speed of light. And we use that velocity addition formula. Okay, that's a group. Okay, we have a velocity addition formula with some real numbers. Well, that group is isomorphic to the real numbers with regular addition, but instead of c, we have infinity and negative infinity. So in other words, the speed of light is algebraically playing the exact same role as infinity does. And that makes a lot of sense when you think about it, because the speed of light is constant, or invariant among reference frames. You can think of it as, no matter how much you change your direction or your speed, you're still going to measure it as the same. That has like an infinite nature to it, So algebraically, it's behaving exactly like infinity does.
Yeah,
it's
yeah.
Those groups are the same.
Yeah, that makes sense. Like, as soon as you said it, I was like, yeah, that totally makes sense. And the way that I saw it in my head is, if you're in your own reference frame, it's kind of like reaching the speed of light is infinitely that way and infinitely in all directions, but then someone can whiz by you and be going at a constant speed, and then in their frame it's still on the horizon everywhere that you'll never actually be able to reach it, just like infinity.
If you think of shooting a photon out and you're like, okay, I'm gonna catch up to it, none of your speed does not matter. It's always traveling c faster than you. Right, so it's kind of like that. It's playing an algebraic role of infinity.
Also, like that, infinity is directly related to like the the dilated time, because as you go closer to c, your dilated time approaches infinity. So like that's also a way to kind of connect the two dots. I guess the negative c doesn't really apply here, because I guess negative speed doesn't really work with the whole time argument, but. Right, just going positive C.
Yeah, it's just representing the other direction. But maybe y'all can confirm this. So I think Andrew Dotson told me this, that if you substitute infinity into... Wait, how did he say this? Like something like if you substitute infinity into like Newtonian transformations, you recover the Lorentz transformation. I'm probably saying that completely wrong. But basically, like... The relation between the Lorentz transform and like a Newtonian transform is that C is playing the role of infinity, and so you can recover. I'm gonna have to look back at what he said so I can relay the message more clearly.
I've never heard that, or maybe I haven't, just forgot. But
it's like the speed of light is not infinite, but algebraically, it's infinite in an algebraic way.
Yeah, doing something with because Newtonian doesn't recognize the whole C thing, right? It says, okay, you can go however fast you want.
Right, exactly.
Exactly. So I think limiting Newton to C might produce that is maybe what...
I think that's like right. I think it's something like that. Like if you have the Newtonian stuff, if you let infinity play, it's behaving like C does for the the equations when you take relativity. When you take relativity into account.
I think that kind of does make sense. That kind of would make sense. Again, not that we know how to do it mathematically speaking, but
I could be completely wrong about what I just said.
No, but it kind of makes sense though. It totally, because I know for a fact that Lorentzian can be converted to Newtonian, right? Assuming the whole C because for low speeds. Totally easily, right? That's the whole point of it. It has to. But at the high speed limit, I'm assuming there is some mathematical way to do it. And Andrew probably knows of some way like that. So there might be some knowledge there that's maybe restricting Parker and I, at least, and temporarily from figuring it out. But soon.
100%. So I would love for you to come back onto the podcast another time, talk about more interesting advanced math topics.
Because usually our first episode is like more, sorry to cut you off, Parker, I know you, but usually our first episode is more like, getting to know you. And like we kind of spoke about that a little bit and like understanding your experience. And then if we were to ever hopefully, have another one on where we can get you, then hopefully, we get more into the actual math of it all. Yeah. Like
personally, I'm not very interesting, but I like to talk about a lot of interesting things.
Well, of course. Well, that's what we're here for, right? All of it. So
awesome.
Yeah.
So thank you for coming on the podcast.
Absolutely.
Once
Thank you for having me.
It was an awesome episode, awesome discussion about group theory. This has been episode number 68 of the Math and Physics podcast. Make sure to follow us on Spotify, subscribe on YouTube, come and like the video and do all that kind of stuff. Let us know if you have any questions. on Instagram
Yeah.
at math.physics.podcast. Make sure to check out Epic Math Time's YouTube channel. It'll be linked in the description, as well as some of his videos that we talked about during the podcast. So yeah,
Awesome.
episode number 68. Thanks for listening. I am your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.